what we mean by rotational kinetic energy if you just have a think about that first. So it's, while I'm writing this out, see if you can take a flying guess at what the equation would be for rotational kinetic energy, not knowing anything about how it's derived or how we could get it, but just what would be your best guess at the equation for kinetic energy for something which has got moment of inertia I, a radius r, and it's traveling at omega. What would be your just blue sky guess for rotational kinetic energy? Anna? Half m omega squared? That's one guess. Another blue sky guess for what you think rotational kinetic energy would be. Chris is coming up with half I omega squared. Any other thoughts for rotational kinetic energy of an object, moment of inertia I, rotating at omega, radius r there. Over r. So how to say that, the whole thing? That one there divided by r. Okay. Okay, let's just try this out. So those are our possibilities. If we say that we take that special case of a single mass, instead of saying it's got any moment of inertia, say it's a point mass m at a radius r going round at omega. Let's just see. Firstly, what's the linear kinetic energy of that point mass? It's going to be half mv squared. Again, we can go through that trick of replacing v by omega, omega and r. So v is equal to r omega. So we've got half m r omega all squared, which will be half m r squared omega squared. mr squared for this system here. It's the moment of inertia. So you can replace mr squared by inertia. So Chris, you're absolutely right that for any system, and you can go through a similar process involving integration over successively smaller hoops and things. It is possible. If you want to see how it's done, look it up in a book. But advanced higher, what you need to know is that the rotational kinetic energy is half I omega squared, and it applies for any rotating object, whatever the moment of inertia. So if you've got a wheel or a hoop, let's just see if the units work, because if we've got units for moment of inertia are kilograms meters squared. This is radians seconds to the minus 2, and we're squaring that. I can't honestly see that we're going to end up with units for radians per second here. I can't see that we're going to end up with units that would come up similar to joules here. It's looking a little bit too complicated. So we're going to do a little bit of dimensional analysis to see whether that lot all gives you the same units, the same dimensions as joules. So we're taking kilograms meters squared, multiplying it by, well, radians is a pure number, so we don't need to include that for dimensions in the units. Seconds to the minus 1 squared is going to give us seconds minus 2. Kilograms meters squared, seconds to the minus 2. So you'd have kg ms minus 1 all squared, which is the same as half mv squared. So it's the same dimensions as kinetic energy. So that would work, wouldn't it? The other way that you can think about it is that we've got kilograms times meters per second per second. Now you've got, so it's kilograms times meters per second. Mass times a height times acceleration due to gravity. What's that the same units as? Potential energy, mgh. Okay. The other thing you could work it into is you've got kilograms times meters per second squared times meters. Mass times acceleration is force times distance. What's that equation for? Work done. So all of these units do fit with kinetic energy. So half I omega squared is the rotational kinetic energy of an object, and that's how you can work it out. So all the way, we've got this sort of parallel system of mechanics. We've got rotational, which involves torque, it involves moment of inertia, it involves alpha for the rotational angular acceleration, it involves omega for the angular velocity. So to try that out, I'll get these rolling cylinders out for you to have a look in just a second. But